Es war kein Versehen. Er hat gewartet, bis alle Augen auf sie gerichtet waren. 20 Rekruten sahen zu, wie der Staff Sergeant sein Knie direkt in ihre Rippen rammte. Genau die Stelle, die sie sich in der Provinz Helmand in Afghanistan zertrümmert hatte. Er beugte sich vor und flüsterte so leise, dass es nur sie hören konnte. Mal sehen, ob sie wieder brechen. Elena Vance hat nicht geschrien. Sie hat keine Anzeige erstattet. Sie hat nicht einmal gezuckt. Sie hat einfach nur gewartet. Und als die Nachtübung begann, als die Lichter ausgingen und der Funkverkehr scharf geschaltet wurde, erteilte sie ihnen eine Lektion, die sie nie vergessen würden. Bevor wir euch zeigen, was passiert, wenn Schweigen zur Strategie wird, schreibt uns in die Kommentare, von wo aus ihr zuseht. Denn hier geht es nicht um Rache, es geht um Kontrolle. Und darum, was passiert, wenn man die Ruhe einer Frau mit Schwäche verwechselt. Die Hitze der Mojave-Wüste drückte nicht nur auf die Schultern, sie flimmerte. Sie strahlte vom Sand ab, als würde die ganze Wüste versuchen, rückwärts zu atmen. In Fort Irwin roch an diesem Nachmittag alles heißer als sonst. Nach Patronenhülsen aus Messing, die zu oft abgefeuert und wieder eingesammelt worden waren. Nach Sand, der sich in Metall gefressen hatte. Nach getrocknetem Schweiß auf Camouflage und nach dem Staub, der sich in die Rangabzeichen legte. Lieutenant Commander Elena Vance stand am Rand des Übungsparcours. Stoppuhr in der einen Hand, Klemmbrett in der anderen. Ihre Dienstkleidung war makellos. Die Ärmel exakt eine Daumenbreite unter dem Ellbogen gerollt. Ihre linke Seite war unter der Uniform fest bandagiert. Man sah es nicht, aber sie spürte es bei jedem Atemzug. Eine ständige Erinnerung, die sie tief in sich trug, die aber niemals ihre Haltung korrumpierte. Sie humpelte nicht. Sie bevorzugte keine Seite. Sie stand einfach nur da, das Rückgrat kerzengerade, und beobachtete die Bewegung der Truppe, als wäre es eine Landkarte, die sie selbst gezeichnet hatte. Auf der anderen Seite des Feldes trugen 5 Kandidaten verschiedener Teilstreitkräfte Übungspuppen auf Tragen, bevor sie zum Schleppen von Munitionskisten übergingen. Der Wind peitschte feinen Sand auf, und die Pfeifen von den Wachtürmen hallten alle 40 Sekunden scharf über das Gelände. Auf der fernen Seite des Kurses stampfte Staff Sergeant Briggs über den Dreck, als gehöre ihm der ganze Stützpunkt. Breitwegige Schultern, der vorschriftsmäßige Schatten eines Dreitagesbarts und dieses arrogante Neigen des Kinns, das immer bedeutete, hier glaubt jemand, er könne besser führen als der Offizier, der vor ihm steht. Hinter ihm trotteten Corporal Ortega, stämmig und ohne jedes Gespür für seine Umgebung, und Private First Class Hale, gerade erst 21 und schon so großspurig, dass er seine Übungswaffe schwang wie ein Spielzeug, das er zu früh bekommen hatte. Sie versteckten ihre Verachtung nicht einmal. Muss schön sein, murmelte Briggs laut genug, damit es die halbe Reihe hören konnte. Befehle brüllen, nachdem man ein Jahr im Genesungsurlaub war. Ich will mir gar nicht vorstellen, wie der Feind riecht, wenn man sich so lange hinter einem Schreibtisch versteckt hat. Ortega kicherte. Hale tat es ihm gleich. Eine halbe Sekunde zu spät, sagte Elena nur, ohne aufzublicken. Sie machte sich eine Notiz auf ihrem Klemmbrett. Ruhige, gleichmäßige Striche. Die Art von Strichen, die nicht um Erlaubnis fragen, ob sie gelassen sein dürfen. Briggs hörte nicht auf. Er tat es nie. Ich habe gehört, Sie haben deine Rippen mit Metallplatten wieder zusammengeschraubt. Was haben Sie genommen? Recycelte Feldflaschen? Ortega schnaubte amüsiert. Von ihrem Posten an der Funkstation blickte die Rekrutin Chen auf. Sie hatte das Ende des Satzes mitbekommen. Ihr Blick huschte zwischen den Männern und Elena hin und her, wartend auf eine Reaktion. Es gab keine, aber Chen bemerkte etwas anderes, die Art, wie Elenas Stift über das Papier glitt. Sie notierte nicht nur Zeiten, sie notierte Namen, Positionen, den Winkel, in dem Briggs sich näherte, den Abstand, den Ortega hielt, und die Art, wie Hales Augen die Beleidigungen aufsaugten, als würde er von ihnen lernen. Chen hatte schon oft Ausbilder gesehen, die Notizen machten, aber das hier fühlte sich anders an. Klinisch, wie eine Beweissicherung, nicht wie eine Bewertung. Elena drückte nur auf die Stoppuhr. Nächstes Paar, Tragewechsel, vor und zurück. Die Zeit läuft jetzt. Die Unteroffiziere bewegten sich nur halbherzig. Briggs ließ sich extra viel Zeit, um zur Übungspuppe zu gelangen, und zog seine Stiefel durch den Dreck wie Satzzeichen der Respektlosigkeit. Hale murmelte im Vorbeigehen zu Chen, wusste gar nicht, dass die Navy ihre SEALs jetzt auch als Mängelexemplare ausliefert. Elena Vance bewegte sich näher an das Geschehen heran, um den Griffwechsel zu beobachten. Immer noch kein Kommentar, keine Emotion. Nur der Stift, die Stoppuhr und die Stille von jemandem, der etwas misst, das viel tiefer liegt als Geschwindigkeit oder Form. Es war die Art von Stille, die Menschen nervös macht, ohne dass sie wissen warum. Briggs sah es und grinste, als würde er gerade gewinnen. Die Wüste atmete weiter. Das Messing schwitzte in der Sonne. Aber die Spannung. Die Spannung war Elenas Spezialität. Sie schrie nicht. Sie korrigierte nicht. Sie hielt nur den Daumen über der Stoppuhr und die Augen fixiert. Nicht auf die Fehler, sondern auf den exakten Moment, in dem jemand glaubte, ungestraft damit durchzukommen. Und jeder auf diesem Platz konnte es spüren. Irgendetwas würde gleich zerbrechen. Und es würde nicht ihr Körper sein. Meint das Section 2, Newton's Laws of Motion. If Section 1 was our toolkit of vectors and units, Section 2 is where we actually start building the machine. Isaac Newton's 3 laws of motion are essentially the rulebook for how everything in the universe moves, from a pebble in your shoe to the moon orbiting our planet. And 2. 1. The first law, the law of inertia. In simple terms, objects are lazy. The first law states that an object will maintain its state of motion, whether at rest or moving at a constant velocity, unless a net external force forces it to change. This introduces the concept of inertia, the inherent resistance of matter to changes in its motion. 2.2. The second law, the dynamics of force. This is the big one. It provides the mathematical link between cause, force, and effect, acceleration. It states that the acceleration, Vecken, of an object is directly proportional to the net force, and inversely proportional to its mass, This can also be expressed more generally as the rate of change of linear momentum. 2.3. The third law, action and reaction. Newton's third law reminds us that forces never exist in isolation. They always come in pairs. If object A exerts a force on object B exerts an equal and opposite force on object A. A right arrow B. Right arrow. It's why your hand hurts when you punch a wall. The wall essentially punched you back with the exact same amount of force. It's also the fundamental principle that allows rockets to move forward by pushing exhaust gases backward. Ready to see how these forces do some heavy lifting? Would you like me to write Section 3, Work, Energy, and the Work-Energy Theorem? Section 3, Work, Energy, and the Work-Energy Theorem. While Newton's laws describe how things move, the concepts of work and energy allow us to predict the outcome of that motion without necessarily tracking every millisecond of the process. Think of energy as the currency of the physical world. 3. 1. Defining work. In physics, work has a very specific meaning. It isn't just effort. It is the transfer of energy that occurs when a force acts on an object as it moves through a distance. If you push a wall and it doesn't move, you've done zero work in the physical sense. Mathematically, work, Blard, is the dot product of the force vector and the displacement vector. W is short vec, utasha dot vex, theta, where theta is the angle between the force and the direction of motion. If you pull a sled horizontally, only the horizontal component of your pull does work. 3.2. Kinetic and potential energy. Energy comes in many forms, but classical mechanics focuses primarily on two. Kinetic energy, the energy of motion. If an object has mass and velocity, it has kinetic energy. Potential energy, SLARS, stored energy based on an object's position or configuration. The most common form is gravitational potential energy, which depends on height, dendars, relative to a reference point. AUG is saying, Psalm 3.3, the work-energy theorem. This theorem is the bridge between force and energy. It states that the net work done by all forces acting on an object is equal to the change in that object's kinetic energy. BOS net, delta K and K final, K initial. This is incredibly powerful because it allows us to find the final speed of an object simply by knowing the work done on it. often bypassing the need to calculate complex accelerations. And that covers the basics of energy transfer. Ready to move on to Section 4, Linear Momentum and Collisions? Section 4, Linear Momentum and Collisions. Momentum is often described as mass in motion. While velocity tells us how fast an object is going, momentum tells us how difficult it is to stop that object. It is the bridge between the forces we studied in Section 2 and the energy we explored in Section 3. 4. 1. Linear momentum and impulse. Linear momentum, is the product of an object's mass, and its velocity, Because velocity is a vector, momentum is also a vector, meaning its direction matters just as much as its magnitude. When a force acts on an object over a period of time, it creates an impulse, The Wittem impulse-momentum theorem states that the impulse is equal to the change in momentum. Delta T and delta vec. This is why airbags are so effective. By increasing the time at delta T, it takes for your head to stop. They significantly decrease the average force exerted on you during the impact. 4. Conservation of momentum. One of the most fundamental laws in physics is the law of conservation of linear momentum. It states that if the net external force on a system is zero, the total momentum of the system remains constant. Initial final. This holds true regardless of the internal forces or messiness of the interaction, making it the primary tool for analyzing collisions, recoil, and explosions. 4. 3 elastic and inelastic collisions. While momentum is always conserved in an isolated system, kinetic energy, may not be. Collisions are categorized based on this distinction. Elastic collisions. Both momentum and total kinetic energy are conserved. The objects bounce off each other without any permanent deformation or heat generation, subatomic particles. Inelastic collisions. Momentum is conserved, but kinetic energy is not. Some energy is converted into heat, sound, or internal deformation. Perfectly inelastic. A special case where the objects stick together after the collision and move as a single mass with a common final velocity. Image comparing elastic and perfectly inelastic collisions. We've mastered how objects interact in a straight line. Ready to throw things for a loop with Section 5, Uniform Circular Motion and Gravitation? Section 5, Uniform Circular Motion and Gravitation. Physics doesn't always happen in a straight line. Sometimes it goes in circles, literally. Whether it's a car rounding a curve or the Earth orbiting the Sun, the same fundamental principles of inward-seeking force apply. 5.1, Centripetal Acceleration and Force. When an object moves in a circle at a constant speed, its direction is constantly changing. Since velocity is a vector, any change in direction means the object is accelerating. This is called centripetal acceleration, and it always points directly toward the center of the circular path. According to Newton's second law, this acceleration must be caused by a net force. We call this the centripetal force. It's important to remember that centripetal force isn't a new magical force. It's just a label for whatever force, tension, friction, or gravity, is doing the work of pulling the object toward the center. 2. Newton's law of universal gravitation. Newton realized that the force pulling an apple to the ground is the same force keeping the moon in orbit. He proposed that every mass in the universe attracts every other mass with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance, between their centers, F equals G, where G1 is the gravitational constant, $6.674 times 10, 11 text, A1 text, kg. This is an inverse square law, meaning if you double the distance between two planets, the gravitational pull between them drops to 1/4 of its original strength. 5. 3 orbits, the ultimate free fall. An orbit is essentially a high-speed balancing act. For a satellite to stay in a circular orbit, the gravitational pull of the planet must provide exactly the necessary centripetal force. By setting Fg E follows F scalar, we can determine the orbital velocity required to maintain a specific altitude. Interestingly, the mass of the satellite cancels out. Whether it's a stray bolt or a massive space station, they both need the exact same speed to stay in the same orbit. We've conquered gravity in circles, ready to dive into the rhythmic world of Section 6, oscillations and simple harmonic motion. How? Section 6, oscillations and simple harmonic motion. Not all motion is linear or circular. Some motion repeats itself over and over again about a central point. This is called periodic motion, and its most fundamental form is simple harmonic motion. Down, Aiken. 6.1, Hooke's law and the restoring force. The defining characteristic of SHM is that the restoring force is directly proportional to the displacement from equilibrium and acts in the opposite direction. For a mass on a spring, this is described by Hooke's law. Fs is where chi is the spring constant, stiffness, and barriers is the displacement. The negative sign indicates that the force always tries to pull the object back to the center, This restoring nature is what causes the oscillation. 6. Two kinematics of SHM. Because the acceleration in SHM is not constant, it changes as $, changes. We use trigonometric functions to describe the motion. The displacement x bar t tlom at any time $2 is modeled as plus x minus t ssa was omega tufs users phi. 8 hours amplitude, the maximum distance from equilibrium. Marwal omega term, angular frequency. How fast the cycle repeats, measured in radii chess. For a mass spring system, 1 omega ein is on the card Kims. Find shell phase constant, where the object was in its speaking at $. 6.3, energy in simple harmonic motion. In an ideal system without friction, mechanical energy is conserved. It constantly transforms between elastic potential energy, use, and kinetic energy. Equals total, some frac undertown, got it's a frac. I'm out to in frac. At amplitude, velocity is 0. All energy is potential. Here at equilibrium, ordex is or 0 Potential energy is 0. All energy is kinetic, maximum velocity. Hammer sound 6.4, the simple pendulum. A mass imbalance on a string of length down also exhibits SHM, provided the angle of swing is small, typically less than $15 circ. In this small angle approximation, the period $, of the pendulum depends only on the length and gravity. T 2 pi po square t slice frac wow. Just like the orbital speed of a satellite, the mass of the pendulum bob does not affect its period. A heavy child and a light child on the same swing will have the same period of oscillation. We've mastered the rhythm of oscillations. Ready to see how these vibrations travel through space in Section 7. Mechanical waves and sound. Watched. Section 7. Mechanical waves and sound waves are nature's way of moving energy from one place to another without moving matter over that same distance. When you shout to a friend, you aren't throwing air molecules at them. You're sending a disturbance through those molecules. 7. 1 transverse versus longitudinal waves. Mechanical waves require a medium, like air, water, or a string, to travel. They are categorized by how the particles of that medium move relative to the wave's direction. Some transverse waves. Particles move perpendicular to the direction of wave travel. Either a wave on a guitar string or immersed in the ocean. Longitudinal waves. Particles move parallel to the direction of wave travel, creating regions of high pressure, compressions, and low pressure, rarefactions. Sound is the most common example. 7. 2. The anatomy of a wave. Every periodic wave can be described by a set of universal properties that determine its behavior. Wavelength, lambda plus. The distance between two consecutive identical points, either goes crest to crest or compression to compression. Frequency, Wells, the number of cycles that pass a point per second, measured in hertz as around. Buntan period. The time it takes for one full cycle to estimate one in amplitude. The maximum displacement from the equilibrium position, which relates to the wave's energy. 7. 3. The wave equation. The speed of a wave, depends entirely on the properties of the medium it travels through, like the tension of a string or the temperature of the air. The relationship between speed, frequency, and wavelength is defined by the fundamental wave equation. Lambda. 7. 4. The Doppler effect. You've likely noticed the pitch of an ambulance siren drop as it passes you. This is the Doppler effect, a change in observed frequency caused by the relative motion between the source and the observer. Moving toward a wave crests are bunched up, resulting in a higher frequency, higher pitch. Moving away. Wave crests are stretched out, resulting in a lower frequency, lower pitch. We've heard the vibrations, now let's feel the heat. Ready to dive into Section 8, Thermodynamics and Fluid Mechanics? Now, Section 8, Fluid Mechanics and Thermodynamics. Having explored how solid objects move and vibrate, we now turn our attention to fluids, substances that flow, and the thermal energy that powers the microscopic movement of all matter. 8. Fluid mechanics. Pressure and buoyancy fluids, liquids and gases exert pressure in all directions. Unlike solids, the pressure in a static fluid depends on depth, because of the weight of the fluid above it. Where rho is the fluid density and g is gravity. This leads to the Archimedes principle, which explains why things float. Any object submerged in a fluid is buoyed up by a force equal to the weight of the fluid it displaces. Ions or fluid submerged. Gashi Whitem on 8.2 Fluid Dynamics. Bernoulli's principle. When fluids move, their behavior changes. For an ideal, incompressible fluid, Bernoulli's principle states that as the speed of a moving fluid increases, the pressure within the fluid decreases. Pias by frac tuggerho via tu padorho ganch text splash constant. This principle is what allows heavy airplanes to fly. The air moves faster over the curved top of a wing, creating a low-pressure zone that sucks the wing upward. 8.3. Thermodynamics, heat, and the first law. Thermodynamics is the study of heat, work, and temperature. The first law of thermodynamics, is essentially the law of conservation of energy applied to thermal systems. Delta U equals Q, bar, plow delta U. The change in internal energy, the bank account of energy. Krons, heat added to the system. Work done by the system on its surroundings. 8. 4. Entropy in the second law. While energy is always conserved, first law, the almost second law of thermodynamics tells us that energy has a preferred direction. It states that heat naturally flows from hot to cold, and that the total entropy disorder of an isolated system will always increase over time. This is why you can't build a 100% efficient engine. Some energy is always lost as waste heat to the universe. We've felt the heat and the pressure, ready to wrap things up with the final chapter. Section 9, Electromagnetism and Light. Section 9, Electromagnetism and Light. In this final section, we bridge the gap between matter and energy by exploring the forces that govern the subatomic world and the radiant energy that illuminates our universe. Electromagnetism is the force responsible for everything from the stickiness of tape to the operation of your smartphone. 9.1, Electric charges and fields. Just as mass creates a gravitational field, electric charge, creates an electric field. Avec Unlike gravity, which only attracts, electric forces can both attract and repel. This is governed by Coulomb's law. F(ci versus Karax, Q1 Q2, where Q is Coulomb's constant, dar 99 times 10 power text and mar 2 fast text quantrons. If the charges are the same, they repel. If they are centered opposite, they attract. 9. Two electric circuits and Ohm's law. When charges are forced to move through a conductor, we create an electric current. To keep these charges moving, we need a push provided by a potential difference or spark voltage. The relationship between voltage, current, and the material's resistance. A var is known as Ohm's law. This is the foundational principle for designing every electronic device you use, allowing engineers to control exactly how much energy flows through a component. 9. 3. Magnetism and electromagnetic induction. Moving charges don't just create electric effects, they create magnetic fields. Conversely, a changing magnetic field can induce an electric current in a nearby wire. This is Faraday's law of induction. While math and Planck's frac defined by Montelum. This principle is the backbone of modern civilization. It's how we generate almost all of our electricity in power plants using giant turbines and magnets. 9.4. Light, the ultimate wave. In the mid-1800s, James Clerk Maxwell realized that fluctuating electric and magnetic fields could propagate through space as a wave. We call this an electromagnetic wave, and its visible spectrum is what we perceive as light. In a vacuum, all EMR waves travel at the universal speed limit, approx 3, 0 tr times 10 to the 8 text, from the long radio waves that carry signals to the high-energy gamma rays from distant stars. The electromagnetic spectrum encompasses the vast majority of how we observe and interact with the cosmos. Congratulations! You've completed all 9 sections of this physics primer. Would you like me to generate a comprehensive summary or a practice quiz to test what you've learned?